Dear students, in this video we are going to see 4.3 and 4.4. Now, you see, find integral over gamma e to the power z dz along the upper half of the circle mod z equal to 1 from 1 to minus 1. Actually, this question means to find this integral value, it is purely depends only on the endpoints, means only on the limits. Lower limit is equal to 1, upper limit is equal to minus 1. It does not depend the path. Okay, so that's why this is called independence on path, independence of path. Okay, now integral 1 to minus 1 e to the power z dz is equal to, see here, this limits given in the question. So now write the limits and then write the function e to the power z which is given here, then integrate. So you will get e to the power z again, then substitute the limits, you will get the value minus 2.35. Okay, now you see the second question. Find integral over gamma sine square z cosine z dz along the contour from pi to I. See here what is given here, means path is not defined, but the integral is fully depend on the endpoints, which means the lower limit pi, upper limit I. Okay, so now you see here integral over pi to I sine squared z cosine z dz. Okay, this is what we are going to calculate. But how to calculate this directly? We cannot calculate this directly, so we are using the substitution method. Okay, so now take t is equal to sine z, then find the derivative, you will get dt equal to cosine z dz. That's why here for cosine z dz you are writing dt. Then for sine squared t, see here for sine z, for sine squared z, see for sine z we are putting t, so which means here we will put t square. Okay, then what is this here? See, limits for t, actually given points are limits of z. Now we are writing limits of t. If z is equal to pi, this is the lower limit. If z equal to pi, what is t? 0. How? You put this z equal to pi here, so sine pi is 0, that is for t. Okay, so that you will write here t. Now z equal to I, that is t equal to sine I, that is the upper limit equal to sine I. Okay, so now after that you integrate t squared, that is t cube by 3, t cube by 3. Then write the limits 0 to sine I. Then now substitute the limits, that is sine I whole cube by 3. Actually this is the final answer from this one. But before that, how to find value of sine I power 3? Now what is the value of sine I? First you see here sine z, we know that e to the power I z minus e to the power minus I z divided by 2I. Here you substitute z equal to I. Here you substitute z equal to I. Okay, right, z equal to I. Then you will find this. Then put q. Okay. Before that, here, before apply this rule here, you take one negative as a common factor. That's why you can write e to the power 1 minus e to the power minus 1. That's why here outside minus 1 whole cube. See, from the denominator you take I outside, and here we have cube also. That's why I am writing I cube. So next, for this one I can write sine h z, we have this sine h for z 1. Okay, so that we can write sine h1 for this one. Here we have cube, that's why we are writing sine h cube. Okay, see here minus 1 cube is minus 1, I cube is minus I, so minus 3 in the denominator. Okay, next you write the conjugate of I, that is minus I, multiply by minus I in numerator and denominator. Finally you will get this answer. Okay, but in numbers, say you can find this value in calculator, sine h1, then make it cube, then use divide by 3. This is the final answer for this question. Okay, that's it. Now we see here types of regions. Okay, suppose D is an open region. D does not contain any of its boundary points. D is connected if any 2 points in D can be joined by an arc in D. Okay, actually here what is important, what we are looking to proceed further, D is simply connected. If actually, what is simply connected? We have to know what is simply connected. If it is connected and every simple closed curve in D can be contracted to a point without leaving D. In other words, see, if the region is in the plane simply connected, if the region is in the plane simply connected means that it has no hole and cannot consist of two separate pieces. Okay, you see few example for simply connected. This is simply connected. This is not simply connected. Why? See, this is connected but not simply connected. Connected but not simply connected. Why? Because it has no hole and cannot consist of two separate pieces. See, it contradicts the definition. That's why it is not simply connected. Even this is not connected. See, it is also not connected. Okay, we see few more examples for simply connected. Now you see this one simply connected, this one simply connected, this one double connected region. Okay, or we can say multiply connected domain, double connected domain or region. Okay, now we'll see Cauchy's integral theorem. If f of z is analytic in a simply connected domain D, then for every simple closed path C or gamma, in somewhere, sometimes we use notation gamma over the integration, or sometimes we use C. Both are it's okay. So that's why I write gamma or C in D, in the simply connected domain D. Then this integration is 0. Okay, how? You see here, this is the simply connected domain D. What is C? For every simple closed path C, this is our C. Simple closed path. This is C. Suppose we find the integration over this path for this function, then the value is 0. What is this function? This function is analytic. That is a condition. Okay. Directly we can write integral over C simple closed path. The function f of z is analytic. Then find the integration. Definitely it is 0. Okay. Now we'll see through few examples. Now evaluate the following integrals by applying Cauchy's integral theorem in case applicable. Okay. Now first one, integral over C cos z dz. Okay. Here what is C? Unit circle, that is mod z equal to 1, radius 1, center 0. See here, this is the given circle. Okay. Now what is the first one? The integrand f of z equal to cosine z is analytic. Yes or no? Yes, this is analytic. The given function cosine z is analytic. If you have doubt, you can check this through CR equations. Okay, definitely it is analytic. Okay, but we have to check for the points which is lie inside on the boundary of C is analytic. Yes, this is analytic for all z. Yes, and also the derivative, you check the derivative equal to sine z is continuous. You see, if this function is analytic, definitely derivative exists. So f dash of z equal to sine z is continuous everywhere and hence on and inside C also. Okay, the derivative is also on and inside C. Okay, therefore we can apply the Cauchy's theorem. So what we have to check? Function is analytic. Function is analytic on the given C, on the given condition. Here condition is mod z equal to 1. Then you can write integral over integral over C, gamma or C. Cosine z dz is equal to 0. Okay. Now you see the second question. The integrand f of z equal to secant z is equal to 1 over cosine z. Okay. Actually, f of z equal to secant z is analytic. But if you write secant z equal to 1 over cosine z, see for this particular value, see for z equal to pi over 2 minus pi over 2 plus 3 pi over 2 minus 3 pi over 2, if you substitute here, if you substitute z values here, then the function is not analytic. So at these points the function is not analytic. So that we have to check where these points exist, where these points on the given curve. Okay, now what is the given condition? Mod z equal to 1. But now where these points, see, z equal to pi over 2 minus pi over 2. Pi over 2 is 1.5. Okay, 1.5 is nothing but maybe here. Minus 1.5 is here. So which means this is out of the circle, so no need to worry. See, actually the given function is analytic, but except these points, at these points the function is not analytic because here it will vanish. Okay, so see here, but all these points lie outside the unit circle. Unit circle is your given condition, so that no need to worry. Hence, because we are calculating for the given condition only, we are calculating for the unit circle only. Okay, so that now f of z is analytic and f dash is continuous in and on C, that is here inside the points, and on C in both f of z is analytic and f dash is continuous. That's why we can write integral over C secant z dz equal to 0 by Cauchy's integral theorem. Okay, now what is C? See, the function, the integrand means what is given inside the integral. Okay, that is the integrand. So f of z equal to 1 over z squared minus 5z plus 6. Okay, now you do factorization on this, so you will get 1 by z minus 2, z minus 3. Same, you see here is analytic everywhere. This function is also analytic. You can check through CR equations. But when you substitute z equal to 2 and 3 here, when you substitute z equal to 2 and 3, then the function is not analytic. Okay, but check these points where, see, which lie outside the unit circle. Okay, see, z equal to 2 is will be here, z equal to 2, the 3 is even more far. Okay, so that function is analytic but except at these 2 points. So that actually what we need to apply the Cauchy's integral theorem, we have to check on the given simply connected domain or simply connected region our function is analytic. Yes, that is sure analytic because the given condition is mod z equal to 1. Okay, in the unit circle the function is analytic, sure, but where it is not analytic, at 2 and 3. But 2 and 3 means no need to worry about that because 2 z equal to 2 and z equal to 3 is not in our condition, it is out of the circle. Okay, so 2 and 3 we can neglect. So now the given function is analytic everywhere in and on the given circle. Okay, so it is not analytic only outside the circle at the points 2 and 3. Okay, so now we are sure we can use the Cauchy's theorem. That's why integral over C 1 by z square minus 5z plus 6 dz is equal to 0. Okay, now see the last question. The integrand, what is given in the last question? F of z equal to z bar. Okay, now you check. If you check through CR equations, this function itself f of z equal to z bar is not analytic. See, 3 constraints. See, all the functions are analytic on the given condition, on the given unit circle, mod z equal to 1. But here this is not analytic even in the given condition, mod z equal to 1. Therefore we cannot apply the Cauchy's theorem. Okay, then how we can find the value? See, this is what we did in the last week. Okay, see, to find the integral, see, integral over C z bar dz equal to, we can use the parameterization, which means parameterization for circle we studied in the last video, means last week. See, 0 to 2 pi the limits, and then z equal to e power I theta, then differentiate, so I e power I theta. So here we want, see, f of z equal to z bar, so e to the power minus I theta, then simplify it, means cancel this, then I integral 0 to 2 pi d theta, then integrate, it will become theta, substitute the limits, upper limit minus lower limit, then your answer is 2 pi I. Okay, that's it. We will see the continuation of this lecture in the next video. Thank you.